Okay, I'm assuming everybody can see my screen. This is quite a short talk. I'll be skimming through the slides fairly quickly, but please feel free to come and bother me at the poster session tonight if you've any questions. So I've been working for a few years now with quality diversity algorithms, in particular map elites. And for those who are not familiar with these algorithms, what they do is, rather than optimizing to a single solution, they optimize to an archive of solutions which hopefully are representative of the solution space, and they allow the expert user to make the final choice of solutions. A side effect of this is that when we run these algorithms, we are given large archives of solutions. So what we were interested in was, what can we learn collectively from these archives? Two reasons to do this. One, it might aid our understanding of the problem area if this is a new problem domain that we don't know so well. On the other hand, if it's a problem domain such as the one we're looking at here, which we understand well, it might increase our confidence in the solver, where the relationships in the solver match the expectations of the expert user. Okay, so how did we attempt to generate rules from the archive? We used two methods. We used GP and decision trees. And the problem we were looking at is a microdepot routing problem. We've published about this previously, but very quickly, it's an urban logistics problem that involves finding ways of delivering goods using a mixture of conventional vans to drop goods off at micro depots, and then using walking, cycle, or electric van couriers for the final delivery. And what we're doing is we're basically trying to find ways of making use of the couriers to minimize the overall impact on city centers. There are approximately 9 characteristics to the solution which might be of interest to the expert users. These are things like the emissions, various costs, the time taken, and the use that we make of resources such as micro depots and the various courier types. We had a real world problem to solve based on data in and around the city of Frankfurt. Underlying data comes from OpenStreetMap. The actual delivery problems are based on data from commercial CEP companies. We had 4 usable instances. We created a 5th by simply combining all 4 instances. That gave us 5 related problems. So basically, if you like, 5 different delivery problems, all based in the same geographical area. All results are based on 10 runs. When we run our algorithm, there is a potential archive size of 5 to the power 9. We don't get anything like that number of solutions back, as many of these solutions are infeasible. What we do get, so we run our EA, and our EA produces plans. You can have a look through the paper to find out more about how the EA works. Typically, an archive, if you visualize it using parallel coordinates, looks something like this. Something of a mess. How do you infer rules from that? So we divided up our attributes into outcome variables and problem attributes. Problem attributes are kind of things that are, if you like, set directly by the algorithm. Outcome variables are problem attributes which, if you like, are set as the problem is solved. So the things that might interest an expert particularly are emissions, time, and the various costs. And we want to find out rules. What are the rules that dictate that these particular outcome variables will be low or high? We balance the data sets. We ran the CN2 algorithm, which creates if-then type rules. We then tried genetic programming. We used the rule tree learner, which is part of the FlexGP platform, which can easily be downloaded and run. Very straightforward, very simple to use. It produces rules of the format that you see here. And essentially, we run both methods and you get back 2 sets of rules based on our archive. And the archive we're looking at, it's not just one problem, it's all of our Frankfurt problems. One of the things we realized very quickly was that if you use CN2, which was using a Java library, not a Java, a Python library, and you use FlexGP, you get slightly different sets of stats back from them, and actually doing a proper comparison of the rules is difficult. For that reason, we wrote a very simple standalone piece of software in Java, which would simply take both of the outputs and calculate the precisions. So the precisions that we used for comparing the two sets of rules was in effect an independent checker program. This is what we got back. Now you can look through the paper, look at this in detail, but essentially these were what we termed policies. The transport research people prefer to call them policies rather than rules. What we discovered essentially was that in most cases, in fact, I think in all cases, it was GP that produced the rule that got the highest precision. So we fairly quickly got to the stage where we were getting good results with GP rather than with the older CN2 method. We can go through what we did. We then looked through the policies themselves. Because this is a fairly straightforward problem domain, it is possible in most cases to rationalize the policy, and it passes, if you like, a common sense test. You can actually see, because we understand the relationship between the cost variables, between the cost of various courier types, their emissions they produce, it's possible to very quickly sanity check, if you like, that these rules make sense. But what we did here was we wanted to say, well, what does this match the expectations of a domain expert? So my colleagues in Frankfurt spoke to a CEP planner, and they said to the planner, why do you think each of these 4 factors might be low? And they came back with 3 things they believed. So for emissions, they believed that emissions would be low because of a low number of trucks, that's the conventional diesel trucks delivering, a low number of micro depots, low number of electric vehicles. These were the things they believed. We then went through our policies that we had evolved and say, of the evolved policies, how many of them satisfy these beliefs? What we discovered very quickly was that in each case, the first thing, the majority of beliefs are covered. We tended to find that the first belief was almost always the easiest to cover. So in the case of emissions, most of our policies satisfy the first belief. We thought about that and we realized the reason probably was that these were the order in which the beliefs were written down. The first thing the planner wrote down was probably the most fundamental, obvious belief that occurred to them first. We also had a couple of situations where we didn't cover a rule. So 3, low number of electric vehicles to reduce emissions. Now that was to us counterintuitive. Asking the expert, they said, oh, it's because batteries in electric vehicles produce emissions, low number of electric vehicles, low number of batteries. Now that was interesting because that was something that wasn't in our model. That showed up, this exercise showed up a number of mismatches between the model that we used for optimization in our code and the model that the expert had in their head. And that was probably this highlighting of rules, beliefs that we couldn't satisfy, was probably the single most useful part of this entire exercise. So my 10 minutes is just about up. If you're interested, please feel free to come and chat to us about the at the poster session. And thank you very much.